Sound check, sound check. Audio is good. Let's take a look at video next. And that also is looking good. Okay. Let's mute that, put away the headphones. And let's get started. Sorry, I know I'm like, 15 minutes late, almost on the dot. But hey, better 15 minutes late than postponing it by potentially days. So, today's topic is going to be Newton's law of universal gravitation. It's a new perspective for us when it comes to the concept of gravity. You could say that we were using gravity quite literally on a surface level up to this point, as in we have been using gravity in a sense that only works when you're at or near the surface of a big planet like Earth. Today that's going to change, but before that, let's go ahead and get started on the problem that I left you with from last time. So in this problem, we were told that there is this amusement park ride where the room is some sort of cylinder that's like high in the air, and it starts spinning and it reaches a speed where the tangential velocity of the people, they're going to be spun in such a way that their backs are going to be against the wall of this cylinder, and their tangential speed will be 15 meters per second. The radius of this ride is 3 meters, so I guess it's not going to fit that many people in it. And our job was to determine what? Let me actually pull up the problem and read what it was asking for, because I've forgotten. Probably it's going to ask for the coefficient of friction, right? I think that was one of the things. Is it the only thing, though? Let's see. Yeah, that's the only thing it was asking. What minimum coefficient of static friction is needed to keep the riders of this ride from slipping? Hopefully you were able to figure it out on your own, and this will just be a quick check your work sort of ordeal. But yeah, let's go ahead and do it. So it's really not too bad. These people are going to be in uniform circular motion once this thing starts spinning and the floor drops down from underneath them. So the only thing holding them up will have to be friction. So this person over here, they're going to have a force upward on them, which would have to be the force of static friction. The force acting downward on them, of course, is just their own weight, force of gravity. And they have to have some force acting towards the center of their circular path. And in this case, since they're up against a wall, they're up against a surface, it wouldn't be surprising if there was a normal force pointing away from that surface, pushing against their backs. And that's the diagram. That's all there is to it. So we know that the friction and gravitational force cancel out, otherwise this person wouldn't be in uniform circular motion. To be in uniform circular motion, your net force has to be towards the center. So all forces that are not pointing either towards or away from the center, all forces perpendicular to that direction must cancel out. So I know that net force Y on this person, force friction static minus force gravitational, must be 0. And net force X on this person is just the normal force acting on them, must equal their mass times their centripetal acceleration. we can rewrite force, friction, static, and force of gravity. We're going to assume that the force of friction static is already maxed out because they said what minimum coefficient of static friction. So if it's the lowest coefficient you can have, then we're assuming a condition where the static friction is maxed out. So mu static times normal force minus mg is equal to 0. And then we can just substitute normal force with mv tangential squared over r. So we get mu static mv tangential squared over r minus mg equals 0. We can cancel the m's, and I'll add the g over to the right hand side. So I get mu static times v squared over r equals g, and multiply by r and divide by v squared. So we get mu static equals rg over v squared. And so the minimum coefficient of static friction must be 3 meters for the radius times 9.8 for the acceleration due to gravity, and then divide that by 15 squared. And I'm getting 0.130 and then a bunch of sixes. I'll just say 0.131. Mu static must be 0.131 or higher. And remember that friction coefficients don't have units. There we go. That's not too bad. Oh, speaking of units, there was something I forgot yesterday, just a quick little thing. We can confirm that v tangential squared over r gives us units of acceleration. So if I go ahead and take the centripetal acceleration equation, the units of centripetal acceleration must equal the units of tangential velocity squared over the units of radius. So we get meters per second times meters per second is meters squared per second squared, and then divide that by radius is typically measured in meters. What does that do? That just cancels 1 power of meters, and you're left with meters per second squared. Those are definitely acceleration units, so that gives us just additional confidence that the formula for centripetal acceleration is correct. Now we move on to universal gravitation. So, Newton's law of universal gravitation. What does it say? Newton's law of universal gravitation. Basically, through experimentation, it was determined that the force of gravity is actually not mg, rather, it is equal to the universal gravitation constant big G times the mass of one object times the mass of the other object, if you have just two objects attracting each other through the force of gravity, divided by the distance between them squared. And sometimes you'll see this written as an r instead, so you might also see it. And in fact, you might also see the m's written differently. Something I like to do, because usually we have something really massive, like a very big mass and a very small mass. A lot of times, I just use a capital M and a lowercase m for the two masses, and then you'll see r squared instead of d squared. Same thing. And the reason we sometimes end up using r is because a lot of times the two objects will be something like the Earth and the Moon, and the distance between the Earth and the Moon will basically be the radius of the Moon's orbit around the Earth. So that's why you'll often see R used here instead of D. Same meaning. It's the same meaning. This distance is specifically not the distance between the surfaces of the two objects, but the distance between the centers of gravity of the two objects. And we can talk about that more in the upcoming chapter, especially for the Physics C students who will actually have to calculate center of mass. And, well, you won't really have to calculate center of gravity in either of the physics courses, but I'll talk about that a little bit for the Physics C students when we get to it. But for now, center of gravity, center of mass, we'll pretend that they're the same thing for now. I'll talk about the difference between them when we get to the later chapter. And for Physics 1 students, for now, just assume that the center of mass or center of gravity of an object is at the geometric center of the object. Just exactly right down the middle if the object is symmetrical, and if the object is not so symmetrical, well, you would probably need calculus for that, so I wouldn't expect you to be asked about such objects to begin with. But yeah, this R or D, whatever you want to call it, is the distance between the centers of mass or centers of gravity of the two objects. If I have something like the Earth and the Moon, then it is not this distance. It's not the surface to surface distance. That's wrong. It's the center to center distance. This is what you plug into the denominator of this equation. Okay, what is big G? Big G is just a universal constant. Big G is equal to, it's actually a rather small number, 6.67. Sometimes people like to add a third digit. I think it's 6.673 times 10 to the negative 11. And then what are its units? Ooh, let's figure out the units of this thing. So force of gravity is a force, so we're going to have newtons equals whatever the units of G are supposed to be, times units of mass, so times kilograms squared would be our standard mass units, divided by units of distance squared, so divided by meters squared. And a newton is a kilogram meter per second squared, right? If you remember, for example, net force equals ma, you would have newtons equals m is in kilograms times a is in meters per second squared. So a newton is a kilogram meter per second squared, so we can go kilogram meters per second squared equals units of G. Oops, that looks like a 6. Units of G times kilograms squared over meters squared. Multiply the meters squared over to the left, you get meters cubed, and divide by kilograms squared, and we get units of G are, let's see, kilograms over kilograms squared times seconds squared, and then meters times meters squared, that's meters cubed. And kilograms reduced by a factor of 1. We remove just one factor of kilograms from the top and bottom, and that gives us cubic meters per kilogram second squared. Not really the most physically meaningful unit, but you know, they might ask you something like this on, say, a multiple choice question on the AP exam. And just knowing how to play around with these units to figure out what the units are supposed to be, that is something you can be tested on. They'll just give you a multiple choice, they'll have this as one of the choices, and then the other choices will be basically the same thing but with different exponents, or maybe it'll be flipped and it'll be kilograms seconds squared per meter cubed. Could be a potential wrong answer that they throw in the multiple choice. So yeah, just be ready to do those sorts of problems when and if asked to do them. Now, this value g, like I commented earlier, you can see that it's very, very small. And the fact that it's so small kind of explains why we don't see universal gravitation in everyday life. Because according to this equation, any two objects that have mass have a force of gravity with which they attract each other. My hand can attract this pen. You don't see it, and the reason you don't see it is because the mass of my hand and the mass of the pen are pretty small, and even if they weren't that small, this g, they're multiplied by such a tiny, tiny number that the amount of gravitational force that would exist between my hand and that pen is so small that it's easily overcome by, for example, friction or any other forces that might be acting on my hand and the pen. So we don't see this stuff happening in real life. If you did this maybe in outer space, far away from any interferences, maybe after a couple thousand years, you would see the pen move an inch closer to your hand. Good luck figuring out a way to live that long, though. But yeah, that's why we usually don't see any significant gravitational force unless one of the two objects involved has a really, really large mass, like, say, an entire planet. So if we equate this to mg, if I want to figure out what's the acceleration, because this is a force after all, and I want to figure out what's the acceleration that that force can cause for an object, well, then we can just use Newton's second law there. If this is the only force acting on the object, then we can say that this gravitational force, g mm over r squared, we can just set this equal to ma. I'm saying little m here would be the smaller mass, and then big M would be something like a planet. And so you get the acceleration due to gravity is equal to big G times m over r squared. More generally, though, we would, well, not more generally, the opposite of generally. More specifically, we would call this acceleration a g. It's just not the g that we're used to. It's not necessarily 9.8. So I'll call this g of r, the function g of r, the gravitational acceleration at r distance away from a planet's center is equal to big G times the mass of that planet over that distance from the planet's center squared. Let's test this out for the Earth. So what is G around the surface of the Earth? Well, the Earth is a planet with a mass of 5.98 times 10 to the 24 kilograms. And this is just information you can look up. Usually it's going to be in some sort of table in your textbook, or it will be in an appendix in a textbook, or you can Google it. And some references will disagree with each other slightly on the numbers. I've also seen 5.97 here, maybe with more decimal places, but 5.98 times 10 to the 24 is good enough for our purposes. And then if you're on the surface of the Earth, well, the Earth has a radius, I'll call it r sub e, radius of Earth. R equals r sub e, radius of Earth is, what was it again? I believe it was something like 6.36 times 10 to the 6. Let me open my book and double check. Or 6.38, maybe. Where are you? let's see, mean radius of Earth, 6.38 times 10 to the 6. 6.38 times 10 to the 6 meters. Let's plug those numbers in and see what we get. So if I do, I guess we'll do it over here since we're running out of space. G at radius of Earth is equal to 6.673 times 10 to the negative 11 times the mass of Earth, so times 5.98 times 10 to the 24, all divided by 6.38 times 10 to the 6 squared. A common mistake here for a lot of students to make is calculator mistakes. Be very, very careful when you do 6.38 times 10 to the 6 squared. Remember to put that times 10 to the 6 in the parentheses so that it gets squared along with the 6.38. Either that, or if you don't trust yourself to remember to do that, just get in the habit of squaring the power of 10 separately. So you could do 6.38 squared, and then without plugging it into the calculator, you can just do 10 to the 6 squared is 10 to the 12. And then all you have to square is the 6.38 and tack on a times 10 to the 12. Be very, very careful with your calculator when doing that stuff. I know some calculators have a scientific notation mode where you don't have to use parentheses, it just understands that you're squaring the whole quantity. Check your calculator and test it to see if it does work that way, and make sure you know if that's the case, and also make sure you know if that's not the case. So just be careful with your calculator here. When in doubt, just use parentheses anyway. Using parentheses that you don't need isn't going to hurt. So 6.673 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by parentheses 6.38 times 10 to the 6, close parentheses, and square. And I get 9.80349. I'm getting 9.8 meters per second squared. About what we would expect near the surface of the Earth. About what we would expect. And for fairly negligible distances, we're not going to see much change in this. We're not going to see a lot of change in this. So if let me see, can I? No, the backside of this is already full. New sheet time. So how far do I need to go just to see, for example, a 0.1 difference in the acceleration due to gravity? How far, how much does the distance from the Earth's center need to change in order for that to happen? Let's go ahead and try to figure out that problem. So I'm going to derive a general formula for the difference in acceleration due to gravity between 2 points. I'm going to say g of R2 minus g of R1 equals let's see, it's going to be big G m over R2 squared minus big G m over R1 squared. And if we do, actually, hold on. No, I want to work this a little bit differently. What do I want to do? I want to do R1 is going to be the radius of the Earth, And then R2 is going to be at some height h above the surface of the Earth. So in other words, if this is the Earth, and here's an object on the surface of the Earth at a distance r sub e, or actually I'll start here. So here's an object at a distance r sub e from the center of the Earth, and I climb up into the atmosphere to an altitude of h. I climb up to an altitude of h. Well, then that is going to be a total distance of re plus h. That's going to be a total distance of radius Earth plus h away from the center of the Earth. So that's going to be my R2. And now let's go ahead and make those substitutions and see what we can simplify. So I'm going to factor out the big G and the big M. And then I've got 1 over Re plus H all squared minus 1 over Re squared. That's going to be 1 over... Oh goodness, I guess I'm going to want to multiply this by Re squared over Re squared, and this by Re plus H squared over Re plus H squared. So that's going to be R Earth squared and that's going to be, and times radius Earth squared, almost forgot that, minus radius Earth plus H squared over radius Earth plus H squared radius Earth squared. Okay, now these are like fractions. They have a common denominator, so I can subtract directly. Let's go ahead and FOIL the top. So I get big G, big M, over, I'm just going to bring this denominator, I'm going to factor it out. So that's going to be Re plus H squared times Re squared times Re squared minus Re squared plus 2 Re H plus H squared. Okay, these will cancel out. And I'm left with, wait a minute. Does that actually make sense? Am I going to get a negative here? Oh, yeah, it should be negative because the gravity at the higher altitude is weaker. Okay, yeah, that's right. Okay, so I get negative GM times 2 RE H plus H squared all over RE plus H squared times RE squared. Okay, now if I want to set this equal to 0.1, what is the height going to be? So I'm trying to solve for what H would need to be if this difference is going to be 0.1. So if I want to see a 0.1 change in the acceleration due to gravity, how high do I need to go to see that difference? Let's see. So negative, or rather, yeah, I should set it to negative 0.1 because it would be a 0.1 drop. If I'm looking for an acceleration due to gravity of 9.7, Well, I guess the easier way to do it would have been to just take this formula and set the left-hand side equal to 9.7 and solve for r. So maybe the way I went about this wasn't really the best. But let's do it the hard way anyway. Let's see what we get. 6.673 times 10 to the negative 11. And then mass of Earth is 5.98 times 10 to the 24. And then we've got 2 times 6.38 times 10 to the 6. H plus h squared all over, I don't want to have to write that number every single time. We'll just call it RE plus h squared for now, times RE squared. Isolating h is going to be a bit of a challenge, so I'm going to have to multiply this over to the left-hand side. And then I'm going to basically have to multiply this stuff and distribute it. And I'm going to have something involving h squared over here, and stuff involving h and stuff involving h squared over here. And am I going to have a constant somewhere out here? No, it doesn't look like it, but it does look like I'm going to have some sort of quadratic function in h, and I'd probably have to use the quadratic formula to solve. Okay, let's go back and do it the easy way then. Forget whatever I was doing here. I mean, if you want to still do it the hard way, be my guest, but I wasn't expecting it to get this ridiculous. Okay, let's do it the easier way then. Let's look at 9.7 and set that equal to gm over r squared and figure out what that r is going to be. So that's going to be 9.7 equals 6.673 times 10 to the negative 11 times mass of Earth is 5.98 times 10 to the 24. And we have to solve for r. So multiply by r squared, divide by 9.7, and take the square root. So I'm going to do square root of, so r is going to be square root of 6.673 times 10 to the negative 11 times 5.98 times 10 to the 24 over 9.7. Square root of all that is going to be 6.673 times 10 to the negative 11 times 5.98 times 10 to the 24 over 9.7. And I'm getting a pretty big number here, which is not exactly surprising. Let me switch my calculator to scientific mode so it can type it out for me in scientific notation. So that's 6.4139 times 10 to the 6. I'm going to say 6.41 times 10 to the 6. So r equals 6.41 times 10 to the 6 meters. Now, if I compare that to the radius of Earth, because remember, we're trying to find the altitude, h, not the distance from the center of the Earth. We're trying to find the altitude. Very common point of confusion for students here is forgetting whether the problem is asking for distance from the center of the Earth or altitude. You will either have problems asking for altitude where you'll forget to subtract the radius of Earth from the r that you calculate, or you'll be given the altitude and you'll plug that into the denominator, treating it as the r, and forget to add the radius of the Earth to it. So mistakes could be made either at the very beginning or at the very end of these problems that mention altitude. Be very careful about that. Anyway, if I take this r minus the radius of the Earth, that's 6.41 times 10 to the 6 minus 6.38 times 10 to the 6. 6.41 minus 6.38 is 0.03, so that's 0.03 times 10 to the 6, which is what, 30,000? Hold on. So it would be 3 times 10 to the 4, yeah, 30,000 equals 30,000 meters, give or take. So yeah, you have to go 30,000 meters up into the sky before you see a 0.1 change in the acceleration due to gravity. So what we've been doing up until this point is still pretty valid. It's valid up until not a full 30,000 meters. I mean, we start to see differences in the third decimal place before then, but you could say it's valid enough for about 10,000 meters into the air, I think is a reasonable thing to say. You can say that the acceleration due to gravity is approximately a constant 9.8 meters per second squared for up to about 10,000 meters in height change. But if you're dealing with height changes bordering on that or significantly greater than that, then yeah, Newton's law of universal gravitation is what you're going to need. So that's one thing that changes compared to what we've been doing before, is that for significant enough altitudes, for significant enough changes in height, we will see the acceleration due to gravity changing. Another thing that changes is how we define potential energy, specifically the gravitational potential energy. Because when we were assuming that the acceleration due to gravity was constant, we just said that the gravitational potential energy was equal to what? It would be the negative of the work done by gravity which would be negative the force of gravity, which we just treated as a constant mg, times the change in height h. Well, we can't really do that anymore. We can't really do that anymore. And if you're wondering about the negative sign, if you just think about it, if gravity does work on an object, that means the object is going in the direction of gravity. If gravity does positive work on an object, then the object is going in the direction of gravity, is going down, in which case its potential energy would decrease. So the negative sign does indeed make sense here. So that's for a constant force of gravity, but what about the change in potential energy gravitational for objects that are much farther away? What about if I had, here's your Earth again, and you've got like maybe a low orbiting satellite over here, and let's say it gets moved to a higher orbit over here, and we're talking about like really significant distances in outer space. And we want to calculate the change in its potential energy and maybe even changes in its kinetic energy due to this. Figure out how fast it's moving, figure out if it's in sync with the rotation of the Earth, especially if you want a satellite that like sits above the same point on Earth 24/7, what are known as geosynchronous orbits. those are things that you may have to take into consideration. Actually, we might be able to do that without having to use energy at all. We'll see later. But the point is, you have a different formula for gravitational potential energy in this universal perspective. Potential energy gravitational, the proof of this comes from calculus, so I'm not going to give the proof here. We'll do that for the Physics C students whenever we get back to reviewing the whole course and adding the calculus back into everything. But for now, I'm just going to have you take my word for it that potential energy gravitational is proportional to big G times the mass of one object times the mass of the other object divided by r, but this time not squared. Or d if you prefer to use d instead of r. And the other thing we do is we tack on a negative sign. Because in the universal perspective, our favorite point to choose, the most preferred point to choose as your zero of gravitational potential energy, is actually the opposite of what we do in the, near Earth's surface perspective. Near Earth's surface, we typically like to choose our lowest point as the zero of gravitational potential energy and count up from there. But in the universal perspective, it makes more sense to pick the farthest point from the center of, the bigger object. I guess in this case it would be, let's pretend we're still talking about big M being the Earth and little m being some object near the Earth, some smaller object. In this case, we actually prefer to set the zero of potential energy as far away as possible from the center of the Earth, which would basically be the edges of the universe, basically at a distance r equals essentially infinity. And if you're dividing by a really, really, really big r, then potential energy gravitational is pretty much zero there. So that works really nicely for us. We don't want to set it to zero at the Earth's core because then you have to calculate, GMM over zero, and division by zero is going to cause us a headache, and we don't want to deal with that. So we set it to zero infinitely far away around the edges of the universe, and then as the small object gets closer and closer to the planet, its potential energy, just like from our previous understanding of potential energy, decreases as the object gets closer and closer to the planet. So if we set the farthest point to zero, it makes sense that all other points at lower potential energy than zero will have negative potential energies. So that's kind of the intuition behind the negative sign. And as for the intuition for the formula itself, you can kind of see it still. You can probably kind of see it. It still has the same units. It should still have units of joules. If we take force units times distance units, here we had the force of gravity using the universal gravitation equation. The force is just big G mm over r squared. And if you take that force multiplied by distance, then this is kind of a crude proof, quote unquote. It's not really a proof, but just gives you a little bit of intuition. You can sort of believe that it makes sense if you think of it this way, and then one of the r's cancels out and you're left with GMM over r. You can kind of see it. You can kind of see it, but it's not actually as simple as this. You actually need calculus to prove this once and for all. This is just kind of nonsense, but it just so happens to be the kind of nonsense that gives you at least a little bit of peace of mind if you don't know the calculus. It gives you a little bit of peace of mind that we didn't just pull this out of nowhere. So yeah, our definition of gravitational potential energy is now also changed because of this new perspective on gravity. So I guess we should get started with a few problems before we discuss things any further. Actually, let me think. What do we need to do today? So, we already wrote the formula for universal gravitation, and we just covered the gravitational potential energy formula. Yeah, I guess the rest is just examples for today, and maybe if we finish fast enough, we can talk about Kepler's laws. But let's go ahead and do some exercises with what we know so far and see what we can do with all of this. Let's see what we've got. So here's a problem that says the average distance separating Earth and the Moon is 384,000 kilometers. Distance Earth to Moon is 384,000 kilometers, or 384 million meters. 384 times 10 to the 6 meters. And it says, use the data in the book's data table to find the net gravitational force exerted by Earth and the Moon on a 3 times 10 to the 4 kilogram spaceship, a 30,000 kilogram spaceship located halfway between them. So mass ship is equal to 30,000 kilograms. They wrote it as 3.00 times 10 to the 4 for those of you who care about your sig figs. Whoops. 30,000 kilograms. And they want it halfway between the Earth and Moon. And they want us to look up data in the table. Basically, they want us to look up the mass of the Earth and the mass of the Moon. So mass of the Earth, we already know. Mass Earth, 5.98 times 10 to the 24, as we've seen in previous examples. And then mass of the Moon is what? 7.36 times 10 to the 22. 7.36 times 10 to the 22 kilograms. And that's all the table information that we need for this problem. And then they told us there's a ship placed halfway between them. And it's assumed here that the distances we're talking about are between the centers of the Earth and Moon. So this is your 384 million meters, 384 times 10 to the 6 meters. And then the object is halfway between the two, so something like this. So what's half of 384? Let's see. 192. 192 times 10 to the 6 meters from either side. And we have a spaceship over here. I guess I will draw it like that. Okay, so basically you just draw all the forces acting on the spaceship. You've got two forces of gravity. That's the only thing that's different from what we've done with force before, is that now you can actually have multiple gravitational forces on the same object. So there's going to be a force of gravity due to the moon. And another force of gravity due to the Earth. And you calculate each of those separately, and then you figure out, based on their directions, how they add or subtract, or if you need to do Pythagorean theorem stuff with it, or trig. And then you calculate your net force, you divide by the mass of the object, and you get its acceleration. Or in this case, all it wanted was the net gravitational force, but we could calculate the acceleration if we wanted to. So let's see, force, gravity, Earth is going to be 30,000, or wait, no. Big G, I'm not going to write out the numbers every time. 6.673 times 10 to the negative 11 times mass of Earth. Again, I'm not going to write out the numbers. I'll type them into my calculator later. Times 30,000, the mass of the ship, over 192 times 10 to the 6 squared. And then force, gravity, moon is going to be big G, mass of the moon, times the mass of the ship, over also 192 times 10 to the 6 squared. So I guess, let's see, so force of gravity Earth I would expect to be bigger because the denominators are the same and the G's are the same. The main difference is just ME versus M moon. Mass of the Earth is bigger, so force of gravity due to the Earth is, probably surprising to no one, bigger. So force of gravity Earth minus force of gravity moon would be the net force on the ship. Net force on the ship, and these directly subtract, because if the ship is halfway between the moon, then it's on the line connecting their centers, which is also the line along which the force of gravity is exerted. I forgot to mention this earlier, but I think it just goes without saying that the force of gravity due to Newton's law of universal gravitation is exerted by the centers of gravity of the two objects in the interaction and on the centers of gravity of the two objects in the interaction along the line connecting their centers. Basically, whatever force of gravity the Earth exerts on the spaceship should be directly towards the center of Earth. So I guess the way I drew my spaceship, it would actually have to be kind of down like this, but that's just because I didn't have the foresight to draw my spaceship, closer to around here. But yeah, the force of gravity should just point towards the center of the object that's exerting the gravity. And And in case you're worried about Newton's third law, since we're talking about this, we might as well go all the way. If you're worried about Newton's third law, yes, the spaceship does exert an equal amount of force on the Earth, but the Earth has a lot more mass. So for the same amount of force, you're going to get a lot less acceleration, very negligible. And then whatever force of gravity the moon exerts on the spaceship exerts an equal amount of force of gravity moon on the moon. But again, the moon is way more massive than the spaceship. The acceleration resulting from that is negligible. Plus also you have to take into account other forces that might be acting on the Earth and the moon that might at least partially cancel out these gravitational pulls. After all, there are other planets around and asteroids and the sun and all of that to account for. Anyway, net force on the ship is going to be force of gravity Earth minus force of gravity moon. So it's going to be, they both have G, they both have that 30,000, and they both have a denominator of 192 times 10 to the 6 quantity squared. The main difference between them is one is at mass of Earth while the other one is multiplied by mass of the moon. So let's go ahead and plug all that stuff into our calculator. Big G, 6.673 times 10 to the negative 11, or 6.67 if that's what you prefer, times 30,000, the mass of the ship, divided by 192 times 10 to the 6 squared. I forgot my parentheses, so parentheses 192 times 10 to the 6, close parentheses and square. So there's that. Whoops. And then times, in parentheses, mass of the Earth, 5.98 times 10 to the 24, minus 7.36 times 10 to the 22. And I'm getting a grand total of 320.75. 320.75 newtons, which is not a lot. And I don't expect it to be a lot. I mean, you're 192 million meters away from both. At that distance, I expect the gravitational force to be relatively weak. I mean, if we calculate how much acceleration this is, if you take this net force divided by the mass of the ship, then you get a very, very small acceleration. 320.75 divided by 30K is 0.010691, and then repeating sixes. So yeah, barely over 1/100th of a meter per second squared. All right, let's do another one. Okay, here's one that's more two-dimensional. So it says a coordinate system in meters is constructed on the surface of a pool table, and 3 objects are placed on the table as follows: a 2 kilogram object at the origin of the coordinate system, a 3 kilogram object at 0, 2, and a 4 kilogram object at 4, 0. Find the resultant gravitational force exerted by the other 2 objects on the object at the origin. If it's been a long time since you've heard the word resultant, you might remember the resultant vector is the vector sum. The resultant of 2 or more vectors is the sum of those vectors. So let's go ahead and find, which one was it? The resultant on the object at the origin. Thankfully, they didn't ask us to do it for all 3 objects, because then we would have been here all day. So we have 1, 2, 3, 4, and 1, 2, 3. We don't even need to go that high. I guess I'll mark a 5 here. So we have a 2 kilogram object at the origin. So that's 2 kilograms. We have a 3 kilogram object at 0, 2, so that's going to be over here. 3 kilograms. And a 4 kilogram object at 4, 0, so a 4 kilogram object over here. And it wants the resultant gravitational force exerted by the other 2 objects on the object at the origin. And these are in meters, so this is 4 meters, and this is 2 meters. And we want to find the total gravitational force on this object. They could have easily asked us to find it for all 3 objects, and we would have been here all day. But fortunately, they only made us do 1 object, and even more fortunately, they made us do 1 object where the 2 forces are going to be perpendicular to each other, so it's a quick Pythagorean theorem and we're done. So we're going to have a force of gravity this way due to this object, and then another force of gravity this way due to that object. And I think this one might actually be the larger of the 2. So I'm going to label them objects 1, 2, and 3. And I'm going to say force of gravity of object 2 on 1 is equal to big G M1 M2 over the distance between them would be 2 meters, so over 2 squared. And then force of gravity of object 3 on 1 is going to be big G M1 M3 over the distance between them is 4, so over 4 squared. That looks like a 42 rather than a square. There, that looks a little bit better. Let's go ahead and calculate. Well, I'm going to keep the 6.673 times 10 to the negative 11. I'm going to keep the big G factored out for a second. So M1 times M2, we've got 2 kilograms times 3 kilograms, that's 6 over 4. 6 over 4, that's 1.5. So this is going to be 1.5 G, 1.5 big G. And then between these two, so we've got 2 times 4, that's 8 over 16. So that's going to be 0.5 big G. Okay, so as predicted, this gravitational force is actually larger, which is ironic because I went ahead and drew this one bigger. This is why you should not assume that my drawings are to scale unless I specifically say so. Let me get a sip of water before I continue. Okay. Where were we now? So we've got 1.5 g worth of force this way and 0.5 g worth of force that way. And of course, that's going to result in a two-dimensional net force, a two-dimensional resultant force. So let's go ahead and combine them using Pythagorean theorem. And we're going to get something, well, if I had drawn it with better proportions, we would see that it's at a big angle, an angle greater than 45 degrees, somewhere along that way. So that's going to have a magnitude of the square root of 1.5 g squared plus 0.5 g squared. So net force is going to be the square root, net force on object 1 specifically, is going to be 1.5 g all squared plus 0.5 g all squared, all under the square root. Okay, so that's going to be 2.25 g squared and 0.25 g squared. 2.25 plus 0.25 is 2.5. So square root of 2.5 g squared, or if I take the square root of g squared, that's just a g, so it's big G times the square root of 2.5. Boy, am I glad I did not plug in the value of big G just yet. It pays to wait on plugging in some of the more complicated and repetitive numbers. The messier decimals, it's better to hold off on plugging them in when you can. Soon enough, we're going to be encountering situations where pi shows up a lot in our calculations, and I'm going to practice the same thing there. I'm going to try and avoid plugging in the value of pi, just keep it as pi until as late as I can in the problem, until I feel that I absolutely need to plug in its value. Anyway, 6.673 times 10 to the negative 11, times 10 to the negative 11, times the square root of 2.5 gets me 1.055 times 10 to the negative 10. I get 1.055 times 10 to the negative 10 newtons of force. Very, very, very tiny amount of force. Less than a billionth of a newton. A little more than a tenth of a billionth of a newton. That's the scale we're working at. Now, what if they had asked us, oh, wait, we're not done. Direction. Inverse tangent of the vertical over the horizontal is what I'm going to do to calculate this angle over here. So, inverse tangent of the vertical is 1.5 g over the horizontal is 0.5 g. The g's cancel out, so 1.5 over 0.5 is 3. Inverse tangent of 3. And I am in degree mode, and I'm getting about 71.6 degrees. I'm getting 71.6 degrees, matches my prediction of greater than 45. Now, if they had asked us to do this for one of the other two objects, it would have been a little more difficult, but still doable. If they had asked us to do it for one of the other objects, then let's say, for example, they had asked us to do it for the 4 kilogram object, then we would have to do this. We would have to write this force, which is just the 0.5 g from earlier. And we would also have to figure out this force, the force between the 4 kilogram object and the 3 kilogram object. And for that, we would need to do big G times 3 kilograms times 4 kilograms divided by this distance squared. And this distance squared would be what? It would be 2 squared plus 4 squared. You don't even need to square root because we need the distance squared. So that's one of the saving graces here, is you can do Pythagorean theorem without having to square root at the end when trying to find some of those two-dimensional forces. So we would do that, big G times 3 times 4 divided by the sum of 2 squared and 4 squared, and that would give you this two-dimensional force over here. And then you would have to figure out what this angle is. You could do that by taking inverse tangent of 2 over 4. And then once you know what that angle is, you can do some trig and break this into an upward component and a leftward component. Add the leftward component of that diagonal force to this 0.5 g from earlier, to the horizontal force that we already have, and then the vertical component stays as is. Pythagorean theorem on that vertical component plus the sum of the two horizontals that we had, and the rest plays out the same from there. So it's not too terrible, but it does involve extra steps that you have to look out for. So I've at least described how to do it, so now you know, in case you are asked to find the resultant force acting on each of the objects. Let's take a look at another one. So next question says, use the data from the data table to find the point between Earth and the Sun at which an object can be placed so that the net gravitational force exerted by Earth and the Sun on that object is 0. I believe this is also called the Lagrange point between two celestial bodies. So if we have the Sun and we have the Earth, and we're looking for some point between these two celestial bodies where the net force gravitational is 0. First of all, educated guess, would you expect this point to be closer to the Earth or to the Sun, and why? If the object is going to be placed somewhere along this line, then it's going to have a gravitational force from the Sun pulling it left, and a gravitational force from the Earth pulling it right, and for the net force to be 0, those gravitational forces need to be equal. So we already know that's not at the halfway point, because at the halfway point, the one that wins, as we saw earlier with the Earth-Moon example, the one that wins is the one with more mass. At the halfway point, the Sun would exert more gravitational force than the Earth does. So it's definitely not at the halfway point. It would have to be closer to the Earth, because by being closer to the Earth, by reducing the denominator in your equation, since the Earth has less mass, you have to make up for the decreased gravitational force due to lower mass for the Earth. You have to make up for it by decreasing the distance from the Earth. So it makes sense that the object actually has to be closer to the Earth than it is to the Sun. And we'll just give it a mass of little m. we're going to say that the distance of this object from the Earth is x. We're going to say that the distance of this object from the Earth is x. And if we look it up in our data table, the data table in the book tells us that the distance between Earth and the Sun is 1.496 times 10 to the 11 meters. So this full distance from the Sun to the Earth, this full distance is 1.496 times 10 to the 11 meters, which then means that the distance from the Sun to our object would have to be 1.496 times 10 to the 11 minus x. And now we have everything we need to solve. So there's going to be a force, gravity, Earth, and there's going to be a force, gravity, Sun, and these need to equal each other. These need to be equal to each other. So big G, M, Sun, M, object, over, I guess this would be 1.496 times 10 to the 11 minus x squared. This has to equal big G mass Earth, mass object, over x squared. The mass of the object cancels out, the big G cancels out. And here is another place where students might make a fatal mistake. Well, I mean, it's not that fatal of a mistake, it's just what you notice here could decide the difference between whether you end up doing this the easy way or the hard way. What some students will do here is they will FOIL this quadratic. And then they rearrange the numbers, they cross multiply, and they end up with some quadratic formula that they have to solve. They end up having to use the quadratic formula, which of course is something that I encourage avoiding unless it's absolutely necessary. You remember how often I tried to avoid that when we were doing kinematics? Same ordeal here. So there is, fortunately, an alternative. Here's what you do. Multiply the x squared over to the left-hand side and divide the ms over to the right-hand side. So you get left with x squared over 1.496 times 10 to the 11 minus x squared equals mass of Earth over mass of the Sun. And now you can just square root both sides. The square root here just cancels the squares over there, and now you're just left with x's to the first power. You're left with a simple linear relationship, which is much easier to deal with. So let's see, we're going to have, instead of writing this 1.496 times 10 to the 11 every time, I'm just going to call it capital D for distance, big distance. So we're going to have x over d minus x equals square root mass Earth over mass Sun. If I multiply d minus x over to the right, then I'm left with x equals square root mass Earth over mass Sun. Lengthen that square root a little bit. Times d minus square root mass Earth over mass Sun times x. add this over to the left-hand side and factor out the x. Add this term over here, add this over to the left-hand side and factor out the x. So I get x times 1 plus square root mass Earth over mass Sun equals square root mass Earth over mass Sun times that total distance, and then just divide by the stuff in the parentheses over here, and you get x equals square root mass Earth over mass Sun times d over 1 plus square root mass Earth over mass Sun. And now just plug in the numbers, and also let me draw a line to divide those from each other because that's a little bit unreadable. There we go. Okay, plugging in those numbers. Square root of mass of the Earth over mass of the Sun is what? Square root of... Did I even write down the mass of the Sun? No, I didn't. Mass of the Sun is 1.991, so I'll write it up here. Mass of the Sun is 1.991 times 10 to the 30 kilograms. Okay, so square root of 5.98 times 10 to the 24 over 1.991 times 10 to the 30. That number is 0.001733. I'm going to leave it unrounded for now. So that number multiplied by d multiplied by 1.496 times 10 to the 11 is, let me convert back to scientific mode on my calculator, is 2.59 times 10 to the 8. So I've got 2.59 times 10 to the 8. Actually, I'll just keep it on my calculator unrounded. And then for the denominator, we have 1 plus, I'm going to copy over that number from earlier, the 0.001733. From all that square root business. And I get 1.001733, no surprise there. And then I'm going to take 2.59 times 10 to the 8 with all the other numbers that came with it, divided by, parentheses, 1.001733065. I guess I didn't really need the parentheses there, unless your calculator does what mine does, which is when you switch it to scientific mode, it puts it times 10 to the 0, which I think is unnecessary, but okay. And I'm getting, overall, 2.588 times 10 to the 8 meters. I'm getting x equals 2.588 times 10 to the 8 meters, give or take. Let me see what fraction of the total distance that is. So if I do 2.588 times 10 to the 8 divided by parentheses 1.496 times 10 to the 11, that is 0.00173 of the distance, almost 2 1,000ths of the distance between the Earth and the Sun. So it's significantly closer to the Earth than it is to the Sun. significantly closer to the Earth than the Sun. All right. What else does this book have for us? Well, apart from what's in the book, there's also a type of question that a student showed me last year that was a point of confusion for her, and I'd like to try and do some of those if I can remember to do so today. It's a really simple concept, so it won't be that hard to come up with problems for it. But let me look through here and see if there's anything more that I would like to include. Yeah, that one we've already done something like it. Find the net gravitational force at the halfway point and find the point where the object can be placed for a net force of 0. We just did one of those, and the other one was, I think, the first example we did. So we can skip that one. Here's one. So it says 2 objects attract each other with a gravitational force of magnitude 1 times 10 to the negative 8 newtons when separated by 20 centimeters. If the total mass of the objects is 5 kilograms, what is the mass of each? Backside of that is already filled. Let's grab a new sheet. So we have 2 objects. We don't know their individual masses. I'm just going to call them M1 and M2. They are separated by 20 centimeters, or 0.2 if you convert that to meters. Their total mass is 5 kilograms, so M1 plus M2 is equal to 5 kilograms. And the force that they exert on each other, the force of gravity between them, is equal to 1.00 times 10 to the negative 8 is what it said in newtons. And it says, what is the mass of each object? What is M1? What is M2? So we can do force of gravity 1.00 times 10 to the negative 8 is equal to big G times M1 times M2 divided by 0.2 squared. I can multiply the 0.2 squared over to the left-hand side and divide by big G, and let's see what that does for us. So 1 times 10 to the negative 8 multiplied by 0.2 squared, and then divided by, parentheses, 6.673 times 10 to the negative 11 is 5.994305. I'm going to round that to 6. And the reason I'm going to round that to 6 is going to become apparent pretty soon. I'm going to round that to 6. So I'm going to say M1 times M2 is about 6. Getting 5.99, you can just kind of feel when you do enough problems within a textbook. You can just kind of feel when some of the numbers that you get are very intentional by the author. And this is one of those moments. So M1 plus M2 is 5, but M1 times M2 is 6. Something we can do here is we can solve for one of these masses. Let's say I subtract m2 on both sides, for example, and that tells me that m1 is equal to 5 minus m2. And then take this and plug it in for m1 over here. So I get 5 minus m2 times m2 is equal to 6. If I distribute, then I get 5m2 minus m2 squared equals 6. If I move everything to the left-hand side, then I get 0 equals m2 squared minus 5m2 plus 6. Oh, this is easily factored. If you kept it as 5.99, you'd be stuck having to use the quadratic formula at this point. But if you were quick enough on the uptake to realize that they probably intended for the number to come out as 6, then you would be able to save yourself a lot of hassle. You'd be able to save yourself a lot of trouble. This is going to be m2 minus 3 times m2 minus 2. Minus 3 and minus 2 add up to minus 5 and multiply to positive 6. So m2 is either 3 or 2. Either m2 equals 3, leading to m1 equals 2, or m2 equals 2, which leads to m1 equals 3, since m1 is 5 minus whatever m2 is. 5 minus 3 is 2, 5 minus 2 is 3. Either way, one of the masses is 3, the other is 2. We're done. One of the masses is 2 kilograms, the other is 3 kilograms. And let me include the units in my final answer, because you do lose points for forgetting to include units if the problem is of such type where you'd be expected to know the units. Okay, what else do we have? Well, I think I've exhausted the main list of examples, so how about we do that one type of problem I was talking about a minute ago that a student presented to me. So last year I had a student who showed me a bunch of questions from her AP classroom. And the question was, if I'm remembering correctly, it was of this type, where there were 2 objects of masses m and m, and each object had a radius of r. Each object had a radius of r, and the gravitational force between them, so I'm just going to say that distance, the radius, is, I'll call it capital R. And the force of gravity between them was simply called F, or F0, for example. And then I think the problem was she was given like a number of other pictures, and I think the task was to arrange them from highest to smallest compared to F0, something like that, greatest force to lowest. So one of them was something like they drew an object of mass 2m with a radius of, for example, 1.5 r, touching another object of mass m and radius r, radius r, mass m. And then another one of them was something like 2m 1.5 r touching another object also of mass 2m with radius 1.5 r. And then I think maybe one of them would have, I mean, I'm not copying the exact numbers, but I'm just saying that we had basically objects with different masses from the original setup and different radii. Some were bigger, some were smaller. And then there was, I think, something like 3m with radius 2r. And then an object with radius, I guess we don't really have enough space to write it inside the object. I'll draw it over here, half r, and then the mass was still just 1m, for example. And I think the task was just arrange them in order from greatest gravitational force to highest gravitational force between the objects. The good news is that these objects are touching each other, so we can exactly calculate the distance, or at least in this case express the distance between their centers of gravity. It's just the sum of the radii. Right? If this thing has a radius of 1.5 r, then the distance from here to here is 1.5 r, and then the distance from this meeting point of the two objects to the center of the next object is just the radius of that second object. So 1.5 r plus r, the distance is 2.5 r. Over here, 1.5 r this way, and another 1.5 r that way, that's 3 r. And then over here, we've got 2r this way, and then a half r that way. That's 2.5 r. And now that we know that, we can go ahead and calculate the force. The force would be, for this first one, it would be big G times 2m times m over the square of 2.5 r. Whoops. 2.5 r, close parentheses over here, and square. Here we have 2m times 2m, so big G times 2m times 2m over the square of 3r. And here we've got 3m times m, so big G times 3m times m over the square of 2.5r. And of course, for comparison's sake, I would want to write this one, F0 is going to be big G m over the distance between these is going to be r plus r is going to be 2r squared. And yeah, let's just compare each of these to F0. So this one is going to have a numerator with m squared and a denominator with 4r squared. So this one is going to be big G m squared over 4r squared. We don't even need to bother with the g's here. They all have the same g in them, so that's not really going to be significant in our comparison. But let's see what happens with the m squared stuff and the r squared stuff. What numbers are in front of those? Here we've got g times 2m times m is 2m squared. And 2.5 squared, that's 6.25 r squared. And then here, 2m times 2m, that's going to be 4. So g times 4m squared over, that's going to be 9r squared. And then here we've got 3m times m, so that's going to be 3m squared over 2.5 squared is going to be 6.25, so that's 6.25 r squared. And yeah, just comparing these and ranking them, we've got 1 over 4 essentially is what comes out of this, 2 over 6.25, 4 over 9, and 3 over 6.25. 2 over 6.25 is a little less than a third, which should still be more than a fourth. 4/9, that's almost a half. And then 3 over 6.25, that's also almost a half. So I guess with these we'd have to draw a closer comparison. We'd probably have to resort to our calculators to figure this out, or find a common denominator between these two if you don't have a calculator handy. Let's see, if I multiply this by 4, that would take care of the 0.25. Yeah, let's do it non-calculator. I mean, you'll have a calculator for the entire AP Physics exam, even the multiple choice, but a lot of times with the multiple choice, the pattern I've noticed is that a lot of them are designed so that you don't actually need the calculator if you really know what you're doing and your mental math is decent. You can usually do those problems without a calculator, so if you're having to turn to the calculator, then there's a chance that you might not be on the right track for most of those problems anyway. So if I multiply by 4 over 4, that's going to be 12 over 25. That's going to be 12 over 25. Over here, if I multiply by 4 over 4, that's going to be 8 over 25. Hmm. 12 over 25. I guess I can multiply this by 4 over 4 again. If I multiply by 4 over 4 again, this is going to be 48 over 100. Or 48%, 48 over 100. This is going to be 32 over 100. 4 over 9, if I multiply by 11 over 11, that's 44 over 99, which is not quite the same as 44 over 100, but close enough. And then 1 over 4, that's 25 over 100. So yeah, we can rank these. In fact, the very first example, this one would be the lowest. Oh, actually, they're unexpectedly in order from lowest to highest. This one's the lowest. Next is this at 32 hundredths. Next is this, and the greatest force is this one over here. How about that? Despite the distance being one of the greatest, the increase in mass seems to have outweighed that effect. It would have been nice if I had written an example where the increase in radius is significantly more, is going to have a significantly bigger effect than the increase in mass, but it's not like I can pre-calculate what these problems are going to result in as I'm writing them. I don't have that skill set. Maybe someone else does, but it's not me. Well, there's that taken care of. So if you see that on like your practice questions, that's how you deal with it. It's not actually that bad when you think about it. I think the problem that a lot of students miss with this is that they can just take the sum of the radii to get the distance between the centers of mass. Once you realize that, this isn't actually that bad. Okay, I think it is time to look at the concept of escape velocity. It's time to play around a little bit with energy. Actually, I don't think I want to use this color here. Let me pick another color. How about you? So, escape velocity. What is escape velocity? I guess I'll start writing down here. Escape velocity. This is a concept that is relevant for space travel. This is a concept that's relevant for space travel. So we need to figure out, when trying to send rockets to outer space, we need to figure out what velocity they need to have in order to successfully escape Earth's gravitational field. We need to figure out how much velocity they need to have at launch in order to climb high enough into the air so as not to lose all of their kinetic energy before they're able to, get away from Earth's gravitational field, so that they don't get pulled down after reaching a certain height and just come crashing down. So that's what the concept of escape velocity is. Basically, it's what initial velocity must a rocket have on the surface of a planet, in our case Earth, in order to completely be free of that planet's gravitational field. This is an energy problem. And to solve it, we will use conservation of mechanical energy, because gravity, even in the universal picture, is still a conservative force. Gravity is still a conservative force, and if gravity is the only force acting on an object, then the non-conservative work is zero. Obviously, we do have air resistance and stuff as the rocket tries to escape through the atmosphere, but let's neglect those effects for now. So here's the object. It starts on the surface of Earth, and it has a mass of m, You've got the mass of the planet is big M, and we want this thing to completely escape the gravitational field. Well, technically you don't actually escape the gravitational field of an object until you're so far away that the gravitational force between you and the object is negligible. That happens, well, at an infinite distance away, at a distance of basically infinity. So we are trying to go from a distance of radius of the planet, big R, to a distance of basically infinity. And if we just want the bare minimum velocity necessary to escape, that means we want the bare minimum kinetic energy to escape. So by the time we reach this infinity place, we're not actually going there, but for the sake of calculation, we'll pretend that we are. If I'm just looking for the bare minimum velocity and therefore the bare minimum kinetic energy, then how much energy will I have left over by the time I reach the end? Well, if I'm just putting in the bare minimum, then I will have completely exhausted it once I get to this infinity destination. So there should be no kinetic energy left by the time you get there, if you're just putting in the bare minimum to escape. Having no energy by the time your escape is complete sounds kind of, I don't know, it feels like it defeats the purpose, but that's what we're looking for. We're just looking for the bare minimum. So, what we can say is kinetic energy initial plus potential energy gravitational initial equals kinetic energy final plus potential energy gravitational final so we have 1/2 m v initial squared, which I'm going to call v escape squared, plus gravitational potential energy initial is negative big G, massive planet, massive object, over, in this case we would start at the radius of the planet squared, equals kinetic energy final, should be 0 if we're putting in the bare minimum, plus potential energy final is negative big G, massive planet, massive object, over, I would call it R infinity, and this basically is defined to go to 0. Okay, so that's a 0 plus a 0, and that's a negative. If we just add this over to the right-hand side, then we have 1/2 m v escape squared equals big G, big M, little m over R squared. The mass of the object cancels out. You've probably noticed a pattern with this today, that the mass of the object tends to cancel out a lot the mass of the smaller object, while the mass of the larger object tends to stay in the equation. We'll see more of that when we discuss planetary motion. And we have the 1/2 out here. Let's multiply 2 on both sides and square root, and I get v escape. Let's do it in a different color. I get v escape, velocity of escape, is equal to 2 big G m over, wait a minute, I did something wrong. R, it's not R squared, it's R. V escape is equal to 2 big G big M over big R, all under a square root. So for Earth, what would that be? Let's see, square root of 2 times 6.673 times 10 to the negative 11 times mass of Earth is 5.98 times 10 to the 24 kilograms over radius of Earth is about 6.38 times 10 to the 6, and I'm getting 11,184.48 meters per second. You need to launch at a little more than 11,000 meters per second. Which sounds like a lot, but there is something that people tend to neglect here, which is that you already have some velocity to begin with, even before the rocket thrusters have even started to burn fuel. Even before that, you still have some speed to begin with. Let me ask you this question, and maybe I'll leave you to think about it until next stream. Why on earth do we launch our rockets from Cape Canaveral in Florida? Why Florida? Why not, I don't know, Alaska or Michigan or New York or any of these other places, for those of us living in the United States anyway. Why Florida? Why Florida? What's better about Florida for launching rockets than any other place in the country? I think I will leave you guys to think about that, and we will probably do a problem that involves the answer to that question later. And by later, I mean next time. Now then, I think there was one more thing I wanted to cover. What was it? What am I forgetting? Hold on, I think it's coming back to me. It was... Right, geosynchronous orbits. Geosynchronous orbits. Okay, so let's talk about geosynchronous orbits. And maybe we will wrap up early today. Geosynchronous orbits. I did mention this earlier. So sometimes we want to launch a satellite in such a way that it hovers above a specific point on Earth, which means it needs to orbit around the Earth in such a way that it's always facing that same point. It needs to orbit, in a way that's synchronized with the natural rotation of the Earth around its own axis. So the question is, to what altitude must such a satellite be launched in order to have such an orbit? Oh, wait. No, hold on. No, I don't think we're ready for this. No, because we're going to need Kepler's laws for this. Okay, never mind. Not yet. We're not doing this yet. Not yet. We need Kepler's laws for that. And I think I want to save Kepler's laws for next time. So, is there anything else? Anything else at all that I can do here? Before we do Kepler's laws next time. Well, I suppose I can... Hold on, it's coming to me. I feel it. Oh, I've got it. Let's talk about, and we'll wrap up with this, let's talk about how a freely falling object, air quotes, how a quote-unquote freely falling object can be in uniform circular motion. Basically, here's the problem I'm trying to give you. Let's suppose how do I want to explain this actually? Well, let me pose this question to you. So let's suppose that I have in my hand a baseball, and let's say I want to throw this baseball with some sort of initial velocity. Such that instead of falling to the ground, I throw it at such a high speed that instead of falling to the ground, it doesn't fall to the ground like what we learned in basic projectile motion like this. Instead, its initial velocity is high enough that the gravitational force doesn't pull it down fast enough, and instead just keeps it constantly turning like this. At what velocity do I have to throw my object so that the curvature of the Earth actually starts to matter? At what velocity do I have to throw my baseball, and not very humanly possible, by the way? We'd actually have to have a machine throw the baseball for us in order to see this effect, but how fast would, and we'd also have to remove the atmosphere and get rid of all air resistance also to make this work. But how fast, if all of that were possible, how fast would the baseball have to be thrown in order to get sent in an orbit around the Earth, basically, near the Earth's surface, a very, very low altitude orbit? How fast would I have to throw it in order for that to happen? Let's assume that the height above the ground of the baseball from where it's thrown is negligible in comparison to the radius of the Earth. So let's say that the object is at a distance radius of Earth from the center of Earth, plus, I don't know, a meter or two, depending on how tall the person throwing the baseball is. We'll neglect that meter or two. Not important. How fast would I actually have to throw my baseball in order for this to work? Because after all, the force of gravity always points towards the center of the Earth. So it can act as a centripetal force if the object is moving fast enough. If the only force acting on this object, if we neglect air resistance and all that's left is the force of gravity, then when the object is here, force of gravity is pulling it straight down. When the object is over here, force of gravity is pulling it this way. When it's here, force of gravity is pulling it that way, always towards the center of this circular path. It just so happens that the center of the Earth is at the center of this path. So the force of gravity will work very nicely for us as a source of centripetal force, and it's the only force we need here, and the only force that exists on this object. So here, the net force is the force of gravity is equal to mass times, this time it'll be a centripetal acceleration. So if we say big G, mass Earth, mass baseball, over radius Earth squared equals mass baseball times v tangential squared over radius of Earth. Let's see what we can do. We can cancel the mass of the baseball, so it doesn't even matter how heavy or light the baseball is. All that matters is how fast you throw it. And we can cancel 1 power of radius Earth on both sides. And all I have to do now is take the square root. So I'm left with v tangential equals the square root of big G, mass of Earth, over radius of Earth. And so I would have to throw my baseball at square root 6.673 times 10 to the negative 11 times mass of Earth is 5.98 times 10 to the 24 kilograms over radius of Earth is 6.38 times 10 to the 6 meters. Don't forget your parentheses where you need them. And the number I'm getting is 7,908.62. 7,908.62 meters per second. If you throw a baseball that fast, it will not land on the ground. Assuming, again, that you remove the Earth's atmosphere so there's no air resistance, which would allow us to do this cool experiment, but also would deprive us of our ability to breathe, and we'd all be dead unless we were fully prepared for this and wearing spacesuits. It would be probably the last physics experiment we ever see in our lives, but who knows, maybe some of you guys think it's worth it. But hey, we don't have to do this with baseballs because we already see this experiment playing out in real life. All you have to do is look up at the sky at night. It's the moon. Yes, the moon is a freely falling object. The moon is a freely falling object. The moon, let me draw it over here. So here's Earth, here's the moon. The moon is just being pulled straight towards the center of Earth. Why doesn't it fall straight down? Well, because it has some sort of velocity. Because it has some sort of velocity, and its velocity is high enough that instead of getting pulled straight down, the force of gravity tilts its direction instead. And because the force of gravity also changes direction as the position of the moon changes, it just keeps tilting its direction. So the moon tries to fall, but because it's moving horizontally, it misses. So if it's trying to fall down here and it's moving horizontally, then it actually falls sideways like this. And by the time it's here, well, now gravity is in this direction. So it will be moving that way, and it tries to, again, fall sideways and ends up here, and the direction of the gravitational force changes again, and it keeps trying to hit the Earth, but it keeps missing, essentially. And so the end result is that it goes around in circles. And of course, they're not perfect circles because the Earth is moving around the sun and all that. The orbits are more ellipse-shaped than circle-shaped, but we can get away with approximating them as circles for now because the elliptical case is more complicated. It requires more math that we currently don't have. So we're just going to work with the simplifying assumption, and this is true whether you're doing Physics 1 or Physics C. So yeah, we're going to play with circular orbits, even though that's not the entire reality of the situation. But there you go. The explanation for this that I see in textbooks, which is kind of a stupid explanation, is that the moon doesn't hit the Earth because, as textbooks say, the Earth curves away as the moon falls or whatever, which it's a very dumb phrase. Like, you know, whoever came up with that phrase just had their own understanding of what those words meant to them, and they just expected whoever was listening to them to understand what that meant. It doesn't make any sense. I don't like that explanation at all. I get why textbooks go for that. It's because it's short and they don't have to write an entire paragraph, but I'd rather have the entire paragraph actually thoroughly explaining the idea. So if you're asked to explain why the moon doesn't crash into the Earth, try to explain it in a way that doesn't that doesn't resort to using the phrase, the Earth curves away. Please. I think that is it for today, so I guess we're ending early. There was a question that I wanted to ask as homework. What was it? Was it something I wrote earlier? Oh, right, this. Do I actually want to ask this question? No, I think I'll just let you guys think about it conceptually. My question here was about why we launch rockets in the United States from Cape Canaveral and why we prefer that location over other locations in the United States. I suppose you could just Google the answer, but I would rather you take the time to actually think about it first to try and see what advantage that location has. I kind of gave a hint right when I started formulating the question. But other than that, do I have a good problem or two to leave you with involving gravitation? Let me see if I can find something good here. Oh, definitely not that one. That'll give away the answer to my conceptual question. Oh, I guess... Well, I did a video on this last year about, like, the factor of planets and their densities. I guess that's something we could touch on. So, I don't really have a problem for it in my book. I'm not seeing one anyway. But one type of question that tends to show up frequently on, like, the multiple choice of the AP exam is they will ask about things like the force of gravity on the surface of a planet. Force of gravity on Earth's surface is G. Or sometimes they don't even, or not G, hold on. Force of gravity, yeah, the force of gravity on Earth's surface on an object is mg, rather. And, or sometimes they'll just call it F0. Yeah, they'll call it just F0. And they might not even refer to the planet as Earth. They might refer to the starting planet as planet A and have you compare it to planet B. And then they'll say, what is the force of gravity? What is force of gravity on a planet with 4 times the density of Earth, or planet A, and let's say 1/2 the radius. They might ask you something like this. So for this, you would actually need to understand what density is, and density you probably know if you've taken chemistry, or if you've taken just a more general physics course before AP Physics, where you actually got to cover density. But if AP Physics 1 and AP Physics C are your first physics courses and you haven't had chemistry, then you might not be familiar with the concept of density. So let's talk about that real quick. I do have an old office hours video from like a year ago, give or take, that does several examples of this, so I won't dwell on it too long. I'll probably just link it in the iCard in the top right corner of this stream recording once I get around to timestamping and editing the description and stuff. So probably somewhere around Tuesday. But we'll just do this as a very quick example. So density. Density we often represent with a number of symbols. There's different types of density. So there's linear density, which we represent with the Greek letter lambda. There's area density or surface density, which we represent with the lowercase Greek letter sigma. And there's also volume density, which we represent with the Greek letter rho. It kind of looks like a tilted P. And so we can have density by length, area, or volume, and we can have density in terms of mass. That's the most common type of density that you'll hear about. But we can also have things like charge density, or even something that's not really physical, like probability density. If you've looked at, if you've done statistics, or if you just did in like your algebra class a little bit of calculating stuff with the bell curve. What's the bell curve? The bell curve is a graph of probability density. The y-axis here, this is probability density. Probability density. And this is an area density. This is an area density, and that does not fit in there. Oh well, you know what it's supposed to say, even if it's not super legible. And what you would do is you would take the density multiplied by the area of some section to figure out the probability of falling in between whatever these values are. Let's say this is a distribution of people's heights, and the area over here the area under a probability density graph would give you the probability of falling between height A and height B, whatever these heights are supposed to be for this height distribution. So density is basically something spread over a length, an area, or a volume. And that something is usually assumed to be mass, but it could also be something like probability or charge, or, I don't know, grams of peanut butter per surface area of your sandwich bread. There's lots of things you can come up with a density for. But in our case, we are specifically talking about mass density per volume. We're specifically talking about volume density. So density of the Earth, we're going to say density of Earth is equal to the total mass of the Earth divided by the total volume of the Earth. And we're going to assume, for the sake of simplicity, that the Earth is a perfect sphere. The volume of a sphere is 4/3 pi r cubed. So mass of Earth over 4/3 pi radius of Earth cubed. Now, the 4/3 pi isn't really going to be the most important thing here. As we'll see, it cancels out pretty quickly. But we are looking at a planet. Now, we want to compare it to a planet that has 4 times the density of Earth and 1/2 the radius. And we want to figure out the force of gravity on the surface of such a planet. So we've got a planet that has half the radius of Earth and 4 times the density. So planet X, density of planet X, is equal to 4 times the density of Earth, is equal to 4 mass of Earth over 4/3 pi radius of Earth cubed. And what we use this density for is we use it to calculate the mass of this new planet. So once we figure out the volume of this new planet, we multiply that volume by the mass per volume, the density, to get the mass. So mass of planet X over volume of planet X is equal to density of planet X. So multiply by volume to solve for mass. Mass of planet X equals density of planet X times volume of planet X. Mass of planet X equals 4 mass Earth over 4/3 pi radius of Earth cubed, right? That's what we got for density of planet X. For volume of planet X, we will assume that it's also spherical, so that's going to be 4/3 pi radius of planet X cubed. Well, the radius of planet X is the radius of Earth divided by 2, right? Half the radius. So radius Earth over 2 cubed. And as you can see, 4/3 pi cancels out. And what do we have? Mass of planet X equals 4 mass of Earth over radius of Earth cubed is what's left from this part. And then over here, radius of Earth over 2 cubed is radius of Earth cubed over 2 cubed is going to be 8. So radius of the Earth also cancels out, or rather, radius of the Earth cubed cancels out, and we get 4 over 8. We get 1/2. This new planet has overall 1/2 the mass of the Earth. And now that we know that this planet has 1/2 the mass of the Earth, but also has 1/2 the radius, we can calculate force of gravity on planet X is going to be let's see, so it's going to be big G, mass of planet X, mass of the object, over radius of planet X squared, and compare that to F0, which was the force of gravity on Earth's surface, so that's big G, mass of Earth, mass of same object over radius of Earth squared. If I just compare these two, mx we said is 1/2 me, so we've got G times 1/2 mass Earth. And then for the radius of planet X, that's just 1/2 the radius of Earth, and then that squared. So we've got a 1/2 over here and a 1/2 squared in the bottom. 1/2 squared in the bottom is a 1/4, and dividing by 1/4 is the same as multiplying by 4. So we're multiplying by 4, and we're also multiplying by a 1/2 in the top, 1/2 and 4. So overall, we're multiplying by 2. So this divided by this would be 2. So force of gravity on planet X is equal to 2 force of gravity on Earth in this case. And if you want more examples of that type of question, again, I do have that old video that you can either find or you can wait a couple days for me to get around to time-stamping this stream and adding that link in the iCard button in the top right corner, which also, I believe I said this last time and I don't remember if I checked. I believe they now have it on YouTube where it also shows up when you open the description. It shows up as a video recommendation in there with like a clickable thumbnail and everything. But if all else fails, I can also just link it in the description, just post the link outright. But I don't think I had to do that the last time, so yeah, it should be fine just with the iCard. Anyway, that is it for today. So I'm hoping to do the next stream on Wednesday of this week. So you might not have to wait until Sunday. I will go ahead and put that on the calendar for Wednesday. But of course, if anything comes up and it has to be postponed, then it is what it is. So yeah, be on the lookout for that. I'll make it public in a few minutes after I'm done with this. And if I need to push it back, I will just change it and you can go check on it and see what the new date has been pushed back to, if you really, really want to see it live. So I guess I don't really have any homework questions to give you. How about we do this then? How about we do... Oh, I forgot to open the book in a tab. Hold on, let me open that real quick. I knew I was forgetting something today. Well, I mean, we don't really look at the book that often. The OpenStax book, that is. But yeah, let's go ahead and look at... Where is it? Here we go. So if you, of course, go to the course plan under Unit 6, the course plan is linked in the description for those of you who are new here. We can look at some of these conceptual questions and some of these problems and exercises. I see I've starred 17 and 29. So there's probably something special about them, or I just completely forgot the reason why I starred them. But let's go ahead and look. So uniform circular motion and gravitation. If I go to the conceptual questions, let's see how far we can get with these. Rotation angle and angular velocity. Okay, yeah, you can skip that because I'm shoving that into the next chapter, so you can ignore the angular velocity stuff unless you really, really want to learn about it early. You can do that, but I'm leaving it out. And I would hope that past me also decided to leave it out and didn't list any of the questions involving it among the recommended questions in practice. I don't believe I had you guys read on fictitious forces. Yeah, I had you skip 6.4, at least if you're following the course plan. So it looks like up to 6.5, skipping 6.4, you can do most of the conceptual questions, at least the ones that don't mention angular velocity and angular speed. If you see that, just ignore it. We'll learn about it soon in the upcoming chapter. And then in the problems and exercises, same deal. From 6.1 through 6.5, you should find some decent practice questions to try out. And then what were the ones that I starred? 17 and 29. Let me see what is up with those. 17 and 29. 17 says, what percentage of the acceleration at Earth's surface is the acceleration due to gravity at the position of a satellite located 300 kilometers above Earth? I guess I start it because it's one of those altitude questions where people can easily forget to take the radius of Earth into account. Okay, and then the other one was 29. What is going on with 29? A large centrifuge like the one shown in figure 634A, okay, this drawing over here, is used to expose aspiring astronauts to accelerations similar to those experienced in rocket launches and atmospheric re-entries. At what angular velocity is the centripetal acceleration 10g if the rider is 15 meters from the center of rotation? Okay, so past me did not skip this for some reason. Well, for now, all you need to know is angular velocity is equal to tangential velocity divided by radius. Don't worry about what that means yet. We will talk about it in the upcoming chapter. But yeah, if you see anything that mentions angular velocity, it's just tangential velocity divided by the radius of the circular path. So if you get stuck on questions like these, just do that calculation real quick to convert to tangential velocity and continue the problem like normal. That's probably why I start it. Okay, so yeah, I guess that'll be your homework. Just look at questions from the book. And I guess the other thing you can do with angular velocity is you can just read the book instead of waiting on me to explain it. But I just like to save it for the next chapter because I feel like it fits in better there. It kind of just feels like a throwaway topic when you put it in the circular motion chapter. So yeah, no formal homework this time. Just think about that question. Think about that question that I was asking. Why you don't need to put in as much kinetic energy as you think you do to launch a rocket. Depending on where you launch it from, there's something you can take advantage of. What is that thing? And practice questions from the OpenStax textbook for those of you who don't have, a solid real-life textbook. And for those of you who do have your own textbook, just comb through that and see what you can do with the questions there. And if you have any good ones, maybe share them. But that'll be it for me. I hope you benefited from this. Hope you learned a lot. I will see you in the next one.